Welcome to the deep dive. There are some things that are just so fundamental to how we live, think electricity or clean water. You basically ignore them until something goes wrong. Well, our sources today are making the case that semiconductors, those tiny little integrated circuits, they absolutely belong in that same category, sort of the quiet, unseen engine driving everything. So our mission here is to give you a bit of a shortcut, really, into understanding this huge high-stakes industry. We want to unpack where you find these chips, everywhere from your phone to critical infrastructure, and also why is this industry booming like crazy right now? And then maybe touch on the really specialized, almost mind-bending challenges in making these things reliable enough to, well, literally trust with our lives.
And it really is a boom, a massive one. Just to give you a sense of the scale we're talking about here, global semiconductor sales, just in the second quarter of 2025, they hit USD 179.7 billion.
Whoa, hang on. That's just for Q2, not the whole year.
Nope, just Q2. And that was up 7.8% from the quarter before. So demand is really accelerating. And looking forward, the projection for the whole year, 2025, is about USD 728 billion. That's showing something like 15.4% annual growth. It's huge.
Okay, so what is a semiconductor, fundamentally, for anyone needing a quick refresher?
Right. So basically, it's a material, usually silicon, that's been heavily processed that lets us control the flow of electricity very, very precisely. It's not like a wire that just lets current flow or rubber that blocks it. A semiconductor can switch between conducting and insulating. And that switching capability allows us to build billions, literally billions of tiny circuits that make up the intelligent systems powering everything.
Got it. Okay, let's start with where most of us interact with this tech constantly, in our pockets, right? If you're listening to this on a smartphone or maybe a tablet, you're holding something called a system on chip, or SoC.
Mm-hmm.
And I think most people hear chip and think it does one specific thing.
Yeah.
But in SoC it's like the ultimate consolidation, isn't it?
Yeah. Exactly. Think of it less like a component and more like an entire computer system squished onto a tiny piece of silicon.
Yeah.
It's got the main brain, the CPU cores, the graphics processor, GPU, often AI accelerators now, memory controllers, all the input-output stuff.
Yeah.
It's all integrated.
And the numbers are just wild. The sources mention modern sockets built on like 3 nanometer or 5 nanometer processes
Tiny.
can have tens of billions of transistors.
Yeah.
Billions. That density is what gives us the power we have now, right? That parallel processing capability.
Precisely. That level of integration and density is, well, it's kind of astonishing. But the challenge then becomes efficiency.
Right.
Which brings us right into your home, the whole Internet of Things, or IoT explosion.
Smart thermostats, speakers, lights.
Exactly. All those hubs, voice assistants, sensors, they need to be always ready, always listening, but you can't have them sucking down power constantly.
Especially if they're battery powered.
Right. So that requires some pretty clever engineering. They use specialized low-power techniques, things like sub-threshold logic and power gating.
Okay, break that down a bit. Sub-threshold logic.
Think of it like running a faucet at the absolute bare minimum trickle. Just enough to function instead of full blast. It uses the lowest possible voltage to operate, saving huge amounts of energy.
And power gating.
That's like putting automatic shutoffs on different parts of the chip. If a section isn't being used, it gets completely powered down instantly. So they sip power instead of gulping it.
That trickle analogy is great. And it must be even more critical for things we wear, right? Like fitness trackers or smartwatches. Tiny batteries, constant connection.
Absolutely critical. You've got wearables, health trackers. They have super strict power budgets. They need wireless connectivity, usually Bluetooth low energy or Wi-Fi. Plus, they're doing complex stuff like biometrics, heart rate, sleep tracking.
Yeah.
So manufacturers use processes designed for very low leakage, and they often embed memory or even small neural processing units, NPUs, right there to handle sensor data efficiently.
And this isn't just the fancy stuff. We forget about the basic appliances too, don't we?
Oh, yeah. Your washing machine, your HVAC system, your refrigerator, they all have microcontrollers making them smart. It's pervasive.
Okay, so let's circle back to that initial idea. If these are as vital as water, what happens if they just stop? If the chips go offline?
Well, the impact would be immediate and severe. It's not just, oh, my phone doesn't work.
Right.
We're talking about potentially catastrophic failures. Internet traffic would grind to a halt. Controlling energy grids, forget it. Personal devices, obviously disabled, but also key infrastructure, financial systems, municipal services. So much relies on this constant background processing. It would be chaos.
Okay, that's sobering. And it perfectly sets up the next area. High-stakes applications where failure just isn't an option. Let's talk transport.
Yeah, a huge role.
Ours used to have maybe a chip for the radio. Now, modern vehicles are basically rolling data centers.
Distributed supercomputers, yeah.
You've got the obvious stuff like infotainment, touchscreens, getting updates over the air. That takes processing power. But the really demanding part is the advanced driver assistance systems, ADS.
Definitely. ADA is where the requirements get really interesting. You're processing data from radar, LiDAR, cameras, fusing it all together.
In real time.
In real time. And it needs not just speed, but what's called deterministic compute.
Deterministic, meaning?
Meaning it's predictable,
Oh.
guaranteed. If the system calculates brake now, that command has to execute within a fixed, incredibly short time frame every single time, no matter what else the system is doing. Lives depend on that predictability.
Wow. Okay.
And then you add electric vehicles, EVs, into the mix. They need robust chips for battery management, controlling the high-power inverters, running complex motor algorithms.
Handling huge amounts of power safely.
Exactly. High voltage, high current, but also needing fine-grained digital control. It's a tough combination. And looking ahead, fully autonomous driving, that just multiplies the need for compute power, redundancy, fail-safe systems exponentially.
That level of required
Well,
perfection almost.
yeah.
It sounds like a testing nightmare. How do they even ensure that reliability? Are they using older, maybe slower, but more proven chip tech for cars?
That's a really sharp question. And yes, often they are. There's a trade-off. Automotive chips frequently use slightly older, more mature manufacturing processes, maybe not the absolute bleeding edge like a smartphone chip.
Because reliability trumps raw speed.
Precisely. Reliability and durability over decades in harsh conditions. They have to meet incredibly stringent standards, mainly the Automotive Electronics Council standards, AEC, Q100, and Q200.
AEC Q100 and Q200, what does that involve?
Oh, brutal testing. Intense temperature cycling, baking the chip, freezing it over and over, shaking it violently with vibration tests, lifetime stress tests to simulate years of use. And they have to build fault detection right into the silicon itself. It's designed to last the life of the vehicle under worst-case scenarios.
That kind of rigor must carry over directly into healthcare then, another area with zero room for error.
Absolutely. Modern medicine runs on semiconductors. Think about diagnostic imaging, CT scanners, MRIs, PET scanners. They rely on specialized high-performance analog and digital chips to capture and process really faint biological signals with incredible accuracy.
And then the things that go inside the body.
Right. Implantable devices, pacemakers, insulin pumps, defibrillators, neural stimulators.
These need ultra-reliable, low-power integrated circuits, ICs,
Yeah.
and they have to work flawlessly for how long?
Potentially decades.
Decades.
Yeah.
Inside a person. How do you even design for that?
It's a whole different level. They need to meet medical device standards like ISO 13485, get regulatory approval like FDA 510K. But beyond the paperwork, the chips themselves have to survive things like gamma sterilization, basically blasting them with radiation to make them sterile before implant.
Wow.
And they need incredibly low soft air rates. That means ensuring that random background radiation, which is always present, doesn't flip a bit inside the chip and cause a glitch years later. It's engineering for near immortality in electronic terms.
Okay, so we've gone from pockets to cars to inside our bodies. Let's zoom out again to the truly invisible engine, the infrastructure powering our digital world. Cloud, data centers, networks, finance.
Backbone.
This is where the demand for sheer volume and speed just seems relentless. Powering cloud services, AI model training, high-speed financial trading. It's driving this insatiable need for more computing power, right? More AI chips, faster memory.
Absolutely. The data center segment is a huge driver of that overall market growth we mentioned earlier, the push towards that $1 trillion market by 2030. That reflects something like an 8.6% compound annual growth rate. It's immense.
And handling the massive data sets for AI, especially, requires getting data to the processors incredibly quickly.
Which is where technologies like high bandwidth memory, HBM, become crucial.
HBM, how does that work differently?
Instead of placing memory chips side by side with the processor, like usual, HBM involves stacking memory chips vertically, one on top of the other. Then they're connected directly down to the processor using thousands of tiny vertical pathways called TSVs through silicon vias.
So it's like replacing a single-lane road with a massive multi-lane highway for data.
Exactly. It creates this enormous bandwidth, this huge pipe, allowing data to flood into those power-hungry AI accelerators almost instantly, essential for training large models.
Okay, but speed isn't everything, especially when you're talking about money or sensitive data. Security has to be paramount.
Non-negotiable. Hardware-level security is baked in now. We rely on specialized chips for things like hardware security modules, secure enclaves built into processors, and especially things called trusted platform modules, or TPMs.
TPMs, what's their role?
A TPM is essentially a dedicated, tamper-resistant microcontroller. It's isolated from the main CPU. Its job is to handle cryptographic operations, generating keys, storing them securely, performing encryption. It creates a kind of physical vault on the motherboard for critical security functions. Makes it vastly harder for software attacks to compromise keys or system integrity. Vital for secure banking, data protection, even things like secure boot processes.
So making all these different kinds of specialized chips, the high power ones, the ultra low power ones, the secure ones, the ones with HBM, the manufacturing itself must be incredibly complex and expensive.
Oh, it's the definition of capital intensive. The whole ecosystem hinges on the equipment makers, the companies that build the machines that make the chips.
Right.
Global sales for that semiconductor manufacturing equipment are projected to hit USD 125.5 billion in 2025.
Just for the machines.
Just for the machines. And most of that, about $110 billion, is specifically for wafer fab equipment, or WFE, the really complex stuff.
Like the EUV machines we hear about.
Exactly. Extreme ultraviolet lithography machines, which cost hundreds of millions each, plus incredibly precise deposition and etching tools needed for those 3 or 5 nanometer features. Building and running a modern fab costs billions, and the equipment inside requires constant specialized support, integration, calibration, maintenance. Downtime is measured in millions per hour. It demands perfection.
So that's the state of play now. Incredibly complex, incredibly expensive. What's coming next? What are the big innovations changing the game for the rest of this decade?
Well, a couple of big shifts are happening. One is in materials. We're moving beyond just silicon for certain applications.
Okay.
You're seeing the rise of compound semiconductors. The big ones right now are silicon carbide, CC, and gallium nitride. GIN.
A CC and GaN. Where are they making the difference?
Primarily in power, electronics, and radio frequency, RF. They can handle much higher voltages, higher temperatures, and swoosh faster than silicon.
So what does that mean for us?
It means things like more efficient electric vehicle chargers and drivetrains, smaller, lighter power adapters for your laptop, more efficient 5G base stations that waste less energy as heat. They're enabling big performance jumps in power systems.
Interesting. And architecturally, how we design the chips themselves.
Big changes there, too. A major trend is the move towards chiplet designs and 3D stacking.
Chiplets, like little Lego bricks.
Sort of, yeah. Instead of trying to manufacture one giant monolithic chip, which gets harder and more expensive as they get bigger and more likely to have defects,
Right.
you design smaller, specialized chiplets, maybe one for CPU cores, one for I/O, one for graphics. Then you connect them together very closely within the same package, sometimes even stacking them vertically using that 3D stacking tech we mentioned with HBM.
That's the advantage.
Better manufacturing yields because smaller chips are easier to make perfectly. And it allows you to mix and match technologies, maybe use the most advanced process for the CPU chiplet, but a more mature, cheaper process for the I/O chiplet. More flexibility, lower cost, faster time to market.
Okay, so better materials, smarter designs, all driven by this relentless demand from AI,
Yeah.
edge computing.
Yeah.
It just keeps escalating.
It does. And layered on top of all that tech evolution are 2 big macro trends: sustainability and localization.
Sustainability and chipmaking.
Fabs use enormous amounts of energy and ultra-pure water. So there's a huge push towards green manufacturing, much more aggressive water recycling, shifting to renewable energy sources to power the fabs. It's becoming a major focus.
And localization, building fabs closer to home.
Exactly. Driven by supply chain security concerns and geopolitical factors, you're seeing massive government investments in the US, Europe, Asia to build localized fabs, bringing chip manufacturing capacity onshore or friendshoring it.
Makes sense for resilience.
It does, but it comes at a huge cost, not just the billions in capital, but finding the skilled workforce needed to actually run these incredibly complex facilities.
Which brings us squarely to what might be the biggest challenge of all. You can have the best materials, the smartest designs, the most advanced machines, but none of it works without the people.
Precisely. This is the talent imperative. It's maybe the critical bottleneck for this entire industry.
Really, a skills gap.
A massive one, globally. As the industry races towards, $728 billion and potentially $1 trillion, we simply don't have enough experts. Not enough process engineers, material scientists, equipment technicians who know how to operate in these hyper-specialized clean room environments.
So what's the solution? Just hope more people go into engineering.
It needs a much more focused effort. The sources really emphasize dedicated training programs, intense teamwork, and crucially, practical, hands-on learning. That means heavy investment in hands-on training labs, sophisticated simulation-based learning that can mimic real fab scenarios safely.
Like flight simulators for chip engineers.
Exactly like that. Plus, strong mentorship programs. We need to get the next generation comfortable and confident operating and troubleshooting billion-dollar equipment in real-world conditions.
Wow. So we've gone from the chip in your phone managing your calendar to the safety critical systems in your car, the life-saving devices, the massive data centers running AI, all dependent on these tiny things needing decades of flawless operation. It really drives home that silent engine idea. It's fundamental.
It truly is. And looking forward, the future of everything we think of as modern life connectivity, AI, digital security, and medical breakthroughs, it hinges not just on inventing the next wonder material like cis-C or GaN or perfecting 3D stacking. It fundamentally hinges on solving this talent imperative. We're building systems that demand near perfect reliability for decades, meeting standards like ISO 13485 for medical or AEC Q100 for auto. So the thought to leave you with is maybe this. Managing this nearly $1 trillion industry, ensuring its reliability, it's becoming less a challenge of pure physics and more a challenge of human capital. How do we cultivate, train, and retain the incredibly deep, specialized expertise needed globally to keep these systems designed for decades of perfection actually running perfectly? The whole high-tech future kind of rests on getting that right.